Hi guys, my name is Neil, and this week we are looking at what I have done for lesson number 11 in Paul McWhorter's Arduino with Python series. Last week Paul asked us to play with some LEDs, make some graphics for it, and have some on a breadboard with our Arduino. Now I've had some LEDs with my solution for some time, so I've not had to do much in that department, but where I did spend some time was improving the comms between Arduino and Python. I've also introduced a Watchdog, so let's take a look at what I've got. So first we'll look at the Arduino code. There's three things going on in the Arduino code. First one, which what we'll cover, is the Watchdog. Now what a Watchdog is it's something that is running in the background independent of your software. It's usually hardware assisted, and I think it is in the case of an Arduino, and effectively what it does is if you don't keep kicking it, resetting it, it reboots the Arduino in this case. So the idea is that you have some task in your code to keep resetting the Watchdog, and if for any reason your code stops doing that, the Watchdog gives you a kick. So there's lots of Watchdog libraries for Arduino. I picked one which was simple, to the point, did exactly what I needed, no more, and you want to get the same one as me if you want to use this code. I don't know what the syntax might be for using other libraries. So you need to fire up the library manager. Here we have it here. We search for Watchdog, and then you'll have a few. Adafruit's got one, there's quite a few others that do different things as well. And if you scroll right to the very bottom, the one I've got is the one by Peter Polidoro. I've installed it. It comes with some examples, that's where I've cribbed my code from, but you'll see 3 lines isn't a lot of cribbing. So install it, and then let's look at how you use it. So first thing you do is you include it. Nice and simple. The next thing you have to do is initialize it. So you initialize a Watchdog and you give it a name. I've given mine the name Cerberus. If you want to know where that comes from, go on wiki and look up some mythology. So once you've initialized it, you enable it. There you go, Cerberus enable. Then this is where the clever bit comes. Every period, every so often, you have to reset the Watchdog's counter. If it reaches 1000 milliseconds, it will reset the Arduino. The default is 1000 milliseconds for the timeout period, and the usual industry standards is to reset it twice as fast as that, which is 500 milliseconds. Now as it happens, I've got a 500 millisecond timer going. It's job 9, where I've actually got my heartbeat LED going. So if we scoot down to job number 9, there you go. I've got the heartbeat toggling, and I just put in another command, which is Cerberus reset. So that's it, Watchdog done. Now, the more interesting bit is the CRC checking that I've done. There's 2 halves to this job. First half is, well, we're sending CRC, so that's the transmit problem. Next half is we're receiving them, so it's a receive problem. Now both of them will use the same CRC library in the background. One is using it to calculate the checksum to send, the other one is using it to recalculate the checksum to compare to what is received. Now the checksum I'm using, with following a helpful hint from Keith Lohmeyer, is a CRC8. And there's lots of different flavors of it, different polynomial values they call it. I'm using one that is known as the Dallas or Maxim. I think it was originally Dallas Semiconductors, and they were acquired by Maxim. Anyway, it just boils down to the polynomial you use. The main point is, whatever you use on one side, you have to use on the other side. So I have to use the same algorithm in the Python. So let's have a look at what we need to do for that. The way CRC works is you have to give it a string, and it crunches through the string and produces a byte. As I said, it's a CRC8, which means it's 1 byte, 8 bits. Doesn't mean it's the most robust CRC checksum in the world. There are plenty of chances for collisions, as they're called, when two different messages can produce the same checksum. But it's good enough for my short messages, and it's good enough for learning. So let's talk about this string. I've got some buffers for it. There's a transmit buffer, and we have the receive buffer. The receive buffer we met last week. So here I've now got a transmit buffer because I have to work out the CRC for transmitting as well. Now, the buffers are important because it has implications in other parts of the code. Now let's jump down to where we use the CRC for job number 4 when we're sending a CRC. Now, so say we have to run it on a string. I didn't have a string last week. All my information was being transmitted using serial prints and serial print lines. There was no string. I need to put it in a string, and that's exactly what sprintf does. It prints stuff to a string. So I'm using sprintf, I've given it my buffer where I want to print it into, and I'm giving it stuff I want to print. It's percent formatted. So %d means a decimal value, basically an integer, not decimal at all, an integer, and that's what the pot is. And then we've got %s's for the temperature and humidities. Now, last week they were floats, but the sprintf in Arduino cannot handle floats. It just doesn't support them, so the %f does not work. So you have to take your floats and convert them to strings before you give them into sprintf, and that's what these functions do. So instead of me capturing the temperatures or their humidities straight into a float value, I just capture them and convert them into a string using the decimal, well, I think it's decimal to string float, whatever that means. So it's a strange command. You only need this in Arduino land because everywhere else in C it supports the %f flag, so you just put the % floats straight into the string. So as I'm getting my temperatures and humidity straight into strings, I don't need these floats anymore, so I've got rid of them. I'm using char arrays instead, strings. So what does it do? This is what it does. Prints it into a string, and then sends that string over to my calculate the CRC command, calc CRC8, which returns a checksum. And then with the serial print to the serial line, it prints the transmit buffer, which is all my serial data, my sensor data, puts in a delimiter, which I've chosen an exclamation mark, and then it sends the checksum that it's just worked out. And that's it. Job done. It does that every time job 4 cycle happens, using whatever the other jobs have collected into the string variables. Now, the other side of the equation is when you're receiving a checksum on the end of the command that comes from Python. So last week we had some parsing using the very clever string to token command, and we have a subject and an action. So that is using one delimiter, the command delimiter, which in my case is a comma. But I just did it again. I sent it the whole command. The whole receive buffer, and then it parses out into a command in the checksum, delimiting on the CRC delimiter, which is the exclamation mark. What this bit's doing here is if it has a checksum and the checksum fails, it basically cancels the command, which means the rest of this just falls through. So that's the send and the receive of the CRC. The CRC8 checksum. Now let's have a quick look at the checksum. This is it. This is it in total. It returns a byte and accepts a pointer to bytes. Now that's quite important. Alright. We have strings up here. So before I send the string, I'm casting it to a pointer to bytes. Now, as it stands on its own, the string is, well, it's chars. Chars and bytes are very similar. They're both in Arduino land, they're both 8 bits, and the only difference between them is chars are signed and bytes are unsigned. Now, to keep the code clean and understandable for me, I'm casting it to bytes because I'm not interested in signs. What happens is you get the pointer to bytes, you start reading the bytes out until you hit the null at the end of the string, and then you work through each bit of the byte. This is extracting the bit, and then this is, to be honest, I'm not sure what it's doing. The wiki goes into some sort of polynomial maths. The important bit to note is this bit. That's the polynomial being used, and it's how it's what distinguishes one CRC algorithm from another. So I need to use the same polynomial value, this 8c, hex 8c. I need to use it on both sides, Python and Arduino, and otherwise the checksums won't match, and I'll get a constant fail. Anyway, works out a checksum and returns it. That's it. Nice and simple. So the main interesting action is in jobs 4 and 5. That's where the CRC action is happening. Now let's take a look at what we've done on Python. So let's get rid of Python for you. Get rid of Arduino so you can see Python rather. So here we go. We have got not too much going on. We shall scoot down through. On our way, we shall call past an LED, which I shall show you. Is it meter type? Which one is it? It's the not the bank, it's the next one. Here we go. So this is I've renamed it all to RGB color LED. This is it. This is the LED that Paul wanted for the homework, and all I've really done is given it 4 legs of different lengths. Other than that, it was pretty much there anyway. Scooting down to where we start dealing with the CRC, when this is the CRC that Python is receiving. So last week all we were doing was taking the sensor data and splitting it based on a comma. What we do this week is, first of all, we split it based on an exclamation mark. We may not have an exclamation mark, so this tests if there's an exclamation mark in the packet that's just been received from Arduino, then we'll split it based on that. Sensor data, checksum. If there is no checksum, as in there's no exclamation mark, it just takes the sensor data and makes it equal to the packet. We're assuming that the packet is just CVC data. So we also then calculate the checksum on it, and that's to basically fudge the calculation that comes next. The calculation that comes next says, well, if there is a CRC, we want it to be digits, decimal digits, and then we test to see if the CRC we check equals the CRC that we've just received. If not, then it just drops through, doesn't do anything. If they do match, then the data is valid, and it basically splits it as usual. And here we have the values being dealt with. If it doesn't come across as not a number, we convert them into floats. So that's how it's dealing with the data when it receives a CRC. When it's sending commands, this is what it's doing here. Again, we have to build a string first. So what am I sending over as the command? Well, this week I'm controlling the LEDs on my Arduino, which I will show you in a moment. I'm controlling them with the pot voltage, and I'm giving the transition levels of 30% and 70%, which is 1.5 volts and 3.5 volts respectively. And my range is 0 to 5. So we basically get the action value. What's it going to be? Where are we? Are we in one range, blue, red or green? And then we're checking to see whether it's changed, and then this is where the main work happens this week. we start building the command to send. The command to send is the subject and the action, and then we've got that in a string, and we run the crc8 command on it. They calculate the crc, and then this is where we stick the two together. We've got the command exclamation mark and then the crc, and that's what we encode and send to the Arduino. Not too difficult. Let's have a look at this command. That's what will interest you more. That command is literally, I had the Arduino code side by side and I just wrote this. So it is almost line by line what the Arduino code is. So you'll see the same thing going on here, you'll see the same stuff going on here. The only things that are different is with Python, I can go through each character. I don't have to be checking for the null at the end. Python does all that stuff behind the scenes. Additionally, Python's not as strict on the typing, so I don't have to worry about whether they're pointers to bytes or chars. Python takes care of all that. All I'm really doing is getting the character, getting the ASCII value of it, and then working through it bit by bit and returning the CRC. That's all it's doing. Just say get the Arduino and the Python code side by side, and you will see it will line up almost line for line. So why don't we have a look at it in action? So if we go down to the demo, here you have it. So what you can see is my graphic. So say my LEDs on the board, you can see one of them is lit up at the minute. As it hums, it's the blue one, because the voltage that you can see on the potentiometer is less than 1.5. So as I change the potentiometer, you shall see that the needle moves, the LED changes colour, a different LED lit up on the board, and then if I whack it right round to the end, the red LED lit up. There we go, and down again. All the way down. There we go. And that's it. It's fully CRC'd to and fro. It's only handling a limited number of commands. In the code you'll see there's a link to a site that will allow you to check CRCs. You can pick the bitness of it and the algorithm maxim in this case, and you can type in your message, and then it'll tell you what the CRC8 for maxim should be. I used that when I was checking my code to make sure it was right. And speaking of my code, as usual, you will find it all on GitHub, linked below this video. And if you have any questions or queries, drop them a note, a comment, and I will do my best to help you. Until next time, bye bye.